So here's just a brief agenda of what we're going to be doing today. First, we're going to start out with these specifications, which is kind of the overall vision that we had when we started this project. And then we're going to go into the ARM design and the methodology with which we approached our design, and then how we ended up controlling it, and then the EEG design. And then we'll go into the future work and improvements, and how we believe that this project can be expanded upon, and then we'll conclude from there.
Here are our user specifications. Basically, we wanted someone who's in a wheelchair to be able to reach out and grab something of a weight of around 4.4 pounds, just like someone who could be standing that's about 6 feet tall. And we wanted it to be low power consumption because we're using the onboard batteries, and we want it to be cheap enough for people to afford.
So in designing our project, we decided to go with SolidWorks because it's an industry standard, and also because we had a lot of intricate moving parts. And this was our design, and it was really handy because that's what the machine shop could read and therefore mill out for us. This is the inner workings, the shoulder design. The way that we designed it was we put the motors in the back to so that we could reduce the torque on the load out front over there, and also for a low power consumption we used working gear in the motors so that it would lock in place even when the power was off.
Here are forearm and gripper designs. Up here you can see RC servos, and the first RC servo controls our return to user function, this one here. The second RC servo controls the wrist rotation, and the third one there opens and closes the gripper. And down here you can see the forearm, and we used tubes from Lowe's that were very inexpensive, and then clamped them together with milled parts from Craig.
So we wanted to design an intuitive user interface, so we went with Cindy's favorite, the Super Nintendo controller. The way it works is, as you can see by the timing diagram, it starts off the data transfer with the latch, and with the latch pulse, you get the first bit of data, which is the B button. When it's high, it turns on, and the next serial data goes in with the clock. So it samples all of them using a 16-bit shift register. So this is our SNES controller schematic, what we designated each button to be, and as you can see...
Wait, no. Wait, hold on. Have you guys seen Teera? Because
That's right.
it was supposed to be here like a half an hour ago. We're going to practice this. And
we're missing a number.
Where the hell is Teera?
Would you like to explain how it works, Teera?
Okay. Let me get out of the way so you guys can see. Okay, so we start out with the starting position, with and the button that is being used is, of course, the start button, and it sets us in the node position. Then we can then control the control algorithm that we designed can start from there. Now, after you start in the reset position, you can then control the height by using the directional D-pad up and down. And as you can see here, and it's actually in the original position. motors. We call it the leveler because we can also do this.
It's an auto level function.
It's an auto level function that level itself. So all I have to do is just use the D-pad to increase the height, and the whole motor will just level itself. So you don't have to control it all the time, and you can disable it. And whenever you want, you can reset it to the original position. There are 4 syllables in the gripper itself. Most of them control the wrist function. There is a return to user wrist that we cannot control. It's not user controllable. There is 90-degree wrist rotation that we can control using a Y button. And there's a return position and return object to the user that we can do with this gripper. Once you're done, you just reset it. And gripper control using a directional D-pad left and right to open the gripper. Once you're done, all you have to do is press select, fold it into a folding configuration, and then you can just move on.
Here we have the control system, and at the top here you can see our Robotic DC motor controller. It's pretty much the brawn of our system with 120 amps per channel. It controls our largest motors, and with the potentiometer feedback, we're turning them into servos. Down here you see our Arduino microcontroller, which is the brains of our control system, and it's processing the information in and out as it gets it. Here we have an RC snubber that deals with voltage spikes, and our 80 amp circuit breaker lets the high current through.
Yes, now, initially we were going to investigate a VCI or brain control interface. Now, this is a basic block diagram. We use electrodes to attach to the head, and that would go to an amplifier. And because we have such small signals coming out of the brain, we'd have to amplify to about 4,500 gain. So, big gain. We're talking about like microvolts we need to get up there. From our amplifier, we go to a digital converter, basic A to ADC. And from that, we send the information to the computer so it can do its DSP. So now, we did try to get some electrodes going here. These are active electrodes. Their main component is the TLC272. It's a very high impedance input op-amp. And the high input impedance serves a couple purposes. It's for an isolation, you don't want to be electrocuting yourself, so high impedance will help out there. It's also for, yeah, right, velocity.
Here's the EEG amplifier where we're getting that 4,500 gain. We're starting out with this differential input that comes into this isolation ESD protection circuit, and then from there we go into 3 gain stages. It's pretty simple. Also, there's some filtering going on because we want to try and filter out. We put a corner at about 0.6, and then since the EEG signals come up to about 80, 70, then we have to deal with 60 Hz hum. So we'll just try and filter that from here. For most part, analog up to here, we're pretty good in terms of delay. The problem comes later when we convert to digital. Then we get some pretty severe lag, and which is why it was not feasible to implement on our current system.
Okay, so this is the part that everyone's been waiting for. Demo. Back out here. I have a setup here. We couldn't set up any higher, but that's a can of peas there.